Reinforcement learning is one of the fastest growing fields in the AI space. It underpins so much of what modern AI is built upon, and is pushing our systems to be more accurate and more useful. So today, I'm going to introduce you to reinforcement learning in 3 different speeds. First, I'll give you a hyper-compressed 30-second intro, then we'll go a little bit deeper to understand some complexities, and then I'll give you a full-bore deep dive. Hi, my name is Christopher Sandoval. I'm a product marketing and developer relations expert, and I'm here to help you make your product and your marketing just a little better. And today, I'm here to give you the internet's fastest introduction to reinforcement learning. All right, let's go. Alright, ready for the 30-second hyperlesson? So reinforcement is a type of machine learning where an agent learns to make decisions based on its environment. It gets rewards for good actions and penalties for bad ones. And over time, it tries to figure out the most optimal solution to get as much reward as possible and as little penalty as possible. Imagine a maze where every single time you made the right turn, you were given $1,000. But every single time you made a wrong turn, you were fined $1,000. Now, pretty soon, you would do everything within your power to make sure that you were making the right turn every single time. And that's the easiest way to explain what reinforcement learning is. Whew, okay, that was a lot in 30 seconds, I know. Are you ready for the longer version? Let's dig in. Okay, so that 30-second version might have gotten you the basics, but this is a case where the devil's in the details.
Like, they didn't like it when I said, speak of the devil. Well, I didn't like that either.
The reality is that there are very few problems in the world where left turn is correct and right turn is wrong. As a good example, imagine trying to teach AI how to play chess. There are millions of potential moves, and the move that might be the right move to make now can change when your opponent makes a different move. All of these variables mean that reinforcement learning has to be very comfortable with the sort of gray area. All of these scenarios are fuzzy at best. So reinforcement learning often has to depend on scaled trial and error. It tries something, measures the outcome of that thing, and then based on the outcome of that decision, gets a reward or gets a penalty. And in most cases, the agent is trained to specifically try and maximize the benefit while reducing the penalty. There's a few other parts of the system that we should talk about. So when we talk about an agent, that is the entity within the system that is making a choice. And that choice is often based on an explicit goal. You want to maximize a certain outcome. And generally speaking, that goal is structured like this. Find a strategy that maximizes long-term rewards and minimizes penalties. For instance, in a self-driving car, we can say that the rewards get tied to how quickly we arrive at our destination, or how safe the driving was. Accidents and longer transit times can be tied to penalties. And in that way, we can maximize everything that we want to happen and minimize everything that we don't. It's important to note that we're not actually tying those outcomes to the rewards and the penalties in the system itself. Instead, we typically use a currency or tokens. We say that you have a certain number of this currency, and for every action that you take that we like, you get more of it, and every action that you take that we don't like, you get less of it, or you have some taken away. Now that's just one methodology, but it is a pretty common one. I know it sounds a bit esoteric, but take a 1,000-foot view and it starts to make a little bit of sense. For instance, if you're training a robot to walk on its own, we can measure the amount of centimeters traveled as success. And every time that it fails to exceed its past centimeter travel, or it falls over, or it makes a mistake in movement, we can take away some currency. So in short, reinforcement systems are how we build systems that learn by doing. And it's a field of study that is revolutionizing AI. Okay, so now we have a better view of how this works in the generality. Let's dig even deeper. This is one of those scenarios like quantum physics. The bad news is that you're not going to understand all of this. The good news is nobody understands all of this. So at its core, one of the underlying processes of reinforcement learning is something called the Markov decision process. Now, the Markov decision process, or MDP, is a framework that we can use for complex situational decision making. When the outcomes of a decision are unclear, we can measure their impact on the environment and the state of things, and thereby make a matrix of potential actions and outcomes. Now, this is going to be very math heavy, but hear me out. The way that MVP works is by creating something called a 4-tuple. Now this 4-tuple has 4 parts. S represents the state space, which is basically the possible situations that the agent can be in. The actions that this agent can take are rendered as A, which is all of the decisions that that agent can make within that environment. Now P represents the transition model, which is simply the probability of moving to a new state after a specific action is taken. And finally, the reward function is shown as R, and that assigns a number value for every outcome of that action. So the standard example that we give for MDP is something called the pole balancing model. Imagine a pole balancing on one end in a cart. Now, S is the state of the system. That's things like the pull angle, the angular velocity, the position of the cart, and the speed of the cart's movement. Now, A is the actions that the agent can take. This includes whether we push on the left or push on the right, how much force we apply, how quickly we apply that force. So P is then the transition of the system. Since this is a physics problem, P is largely things like the laws of thermodynamics and Newtonian laws of motion. And finally, R is the reward that we give it for specific states, notably whether the pole is standing or not. And based on this, we can have the agent take a lot of different actions and see what state change that invokes. And from that state change, we can either reward or penalize the system. And the cool thing about the MDP is you can actually layer different algorithms on top of this process. And one such layering is called Q-learning. So Q-learning basically takes every single state and every single action and creates a matrix of potential actions and potential outcomes. Every node in this array basically says, I was in state S, I took action A, and I ended up in state S1, or S2, or S3, or S4. Now this array is based on pretty complex mathematics, but to simplify, this approach calculates the quality of the state-action combination after delta t steps are taken following a specific state. Or to make it even simpler, it makes an array of actions that are taken and what state change resulted. Now the cool thing about this is if you zoom out and look at the Q array, you can actually see a path to the ultimate outcome over multiple steps. And from here, you can make a value judgment or a policy judgment and maximize certain pathways, and thereby certain outcomes. For instance, let's go back to our self-driving car. If we create a Q array, we can see what steps the agent took that increased car accidents, but decreased the time in transit between locations. We can also see the steps it took to decrease car accidents, but increase time between locations. We might even find an array that decreased car accidents and decreased the time in transit. But regardless, we can make a value judgment based on what we want to maximize, and we can demand the system instead optimize the display paths for that specific optimization pathway. And believe it or not, you can layer even more on top. For instance, value-based methods try and find how good each individual action is. It sort of builds a scoreboard and assigns actions a specific score. Now, policy-based methods basically infer rules from the system itself. In other words, it doesn't really keep a score. It just knows that if you see a wall with two options, you want to turn left. If it sees a wall with only a right turn option, you go right. If you see a wall with no turn option, then you work backwards. Going even further, there's a method called actor critic. The critic is like the scoreboard keeper. It observes what actions are being taken and basically criticizes whether that was a good action or a bad action. So the actor is the one that's actually taking the actions. It's the rule maker. It decides what actions to actually take based upon what it's seeing, and they work together. The critic gives feedback to the actor, and the actor tries out actions to either validate or invalidate what the critic has told it. So throughout all of this, you probably noticed some pretty glaring issues with reinforcement learning. And these aren't particular to a certain methodology, they're sort of universal to reinforcement learning on the whole. One of the biggest challenges we face is exploration versus exploitation. The question here is whether we maximize exploration of multiple different states and actions, or whether we exploit something that we know works. Is it good enough to just find one successful path and then hammer that one path? Or do we want to find potentially more optimal solutions? There's also the problem of sparse rewards. Typically in a system that is a game or has some sort of end goal, you get rewarded at the very end. But the agent had to take hundreds of actions to get to that end state, potentially even hundreds of thousands of actions. And in that case, you don't want to reward or penalize it across every single step taken, because then you're just creating so much noise that you're not really going to be able to find the optimal path. But you also don't want to wait until the very end, because then the agent is going to struggle to optimize anything except maybe the last steps in that process. And that's an even more core issue with reinforcement learning. It's really sample inefficient. Reinforcement learning does a lot through trial and error. And if you're playing a game like tic-tac-toe, that's fine. But if you're doing something like cancer detection, you can't really afford to have a million false positives or a million false negatives. So it's a balance to see how much fuzziness you build into the system itself and what you specifically reward. And that rewarding process brings up its own ethical issues. For instance, in the self-driving car system that we were talking about, imagine you have a car with 4 people inside and an AI in self-driving mode. In the crosswalk, you have 4 people crossing. If the car stops suddenly, there could be fatalities in the car. If it doesn't stop, there will be fatalities in the crosswalk. Which choice do you reward in that case? You can't make a value judgment on human lives. So reinforcement learning, despite all these challenges, is core to our AI development process. And it's already making huge waves in a bunch of different industries. It's helping robots learn how to walk. It's doing protein folding to discover new medications for cancer. It's optimizing factory operations to make less pollution. It's even making smarter recommendations on systems like YouTube. The system wants you to subscribe. But the reality is that reinforcement learning is already key for AI development, and it's only going to become more important in the years to come. And that's a wrap on reinforcement learning. We started with the basics, we dug into more details, and we ended with a nice deep dive. If this got you curious about AI and tech, you should like this video and subscribe to this channel. I do this kind of content every single week. If you'd like to see more of my work, you can find me on LinkedIn, Twitter, or Instagram, or here on YouTube. Thanks for watching. I'll see you in the next one.